everyone. Welcome to our Urban Flood Modelling and Risk Management group webinar series. Let's turn your mic off. So today we have a presentation from Duncan Kitts from BME. Give us a presentation on TUFLOW and quadtrees. So if I hand over the floor now to Duncan.
Thanks, Mike. Thanks for the introduction. Thanks also for Albert for inviting me to give a presentation on TUFLOW QPC. Thanks also for the working group for having me and for everyone to giving up their lunchtime to listen to a bit of a talk on TUFLOW QPC, also known internally as Quadtree, and I suspect that will stick externally as well. It's worth from the outset just pointing out that although I will be giving the presentation, my colleague Greg Cullicutt is very much the brains behind TUFLOW QPC and Quadtree. He's the one that's done most of all the coding for this, and he's also helped me put together a number of slides, which I'll be showing you over the course of this presentation. Greg is based in Brisbane in Australia, so due to time zones, it wasn't practical for him to give a presentation, so that honour has fallen to me. But I just very much want to make sure that Greg takes a lot of credit for the work for this. I just want to give a bit of a story as to how we got to TUFLOW Quadtree. So probably the product that we're most well known for is something that's now being rebranded internally TUFLOW Classic. This was first developed in 1989 as a joint venture between BMT and the University of Queensland in Brisbane, and has been continuously developed ever since. TUFLOW Classic is a fixed grid implicit finite difference solution which solves the full 2D shallow water equations of mass and momentum. And since 1989 it's been used throughout the world and been used to simulate hydrodynamics in a large number of urban and estuarine and fluvial environments. It's been integrated with various 1D schemes, so schemes such as Flood Modeler and XP Swim, amongst others, and it's also been integrated with our own TUFLOW 1D scheme. It's extremely well benchmarked and well respected. One limitation is that the finite difference scheme is limited to running on a simulation on a single core. The implicit nature of the matrices used to solve the 2D equations means that there are various interdependencies, which means that parts of the computation cannot be distributed across multiple cores or onto things such as GPU cards. And this limits the speed of the simulation and also makes very large model domains quite impractical. So we started looking at explicit finite volume schemes. Finite volume methods are generally considered to have a number of advantages in terms of conservativeness and conceptual simplicity. They are much more intuitive. The explicit scheme means that the calculations are independent. The scheme is volume and momentum conservative and allows the representation of flow discontinuities and changes between gradually and rapidly varying flow. First and second order spatial solutions are the most common, and these allow sharp gradients to be represented. So we're very much representing the underlying physics here. Probably where they come into their own is that explicit finite volume schemes are much more suited for parallelization, which allows distribution across multiple CPU or GPU cards. This led to the development of TUFLOW HPC, which is a second order explicit finite volume scheme. The HPC stands for heavily parallelized compute, and this was released in 2017 and allows users to run simulations across multiple processors and GPU cards, leading to much quicker simulations. And that's been used ever since for a variety of studies. However, as soon as you allow simulations to be run on multiple processors or on GPU cards and thus speed up simulation times, users want two things really. They want to create ever bigger models or they want to run more of them. A very good example of this is a project that BMT, with other project partners, was involved in for the Environment Agency Reservoir flood mapping. So back in 2008, there was an original national programme of reservoir inundation mapping for England and Wales. Over 2,000 reservoirs were analysed, but at the time only 147 were identified as high risk and required modelling with full shallow water equations. At the time, it wasn't considered feasible to do the whole 2,000 reservoirs in full shallow water equations. Since then, we've seen numerous improvements in terms of hardware, so GPU cards are much more prevalent. Software, we now have products such as TUFLOW QPC, and also input data, things such as DTMs. So 3/4 of England is covered by very high resolution LiDAR imagery. So we're talking 2 meter, 1 meter, 0.5 meter, and even 0.25 meter resolution. And that data is freely available via the EA Open Data Portal. So where we have that data available, people want to use that kind of resolution. So with the improvements in hardware, software, and input data, there was an updated specification, an updated project for reservoir flood mapping, which required the simulation of all 1,865 regulated reservoirs in England to that updated specification. Each of those reservoirs were then run for 3 scenarios: a dry scenario, a wet scenario, and a fluvial scenario. The wet scenario involved running the dam break with a 1 in 1,000 year flood downstream. So in total, there were 5,600 scenarios. For the current project, a bespoke DTM was created, and that was part of the specification. And that was simulated using a 2 meter grid size in the TUFLOW model. Just as a comparison, the model cell size in the original National Reservoir Inundation Modelling project was 5 to 20 metres. The very nature of reservoir flood modelling means that the domains of some of these models are very, very large, and that presented a lot of challenges in terms of scheduling the simulations, running them, but also the sheer amount of data that was generated. So run times were 6 to 100 times slower than the original national programme, and model output sizes were 6 to 100 times larger. So the question is, although that 2 meter detail is quite useful in channels, around structures and particular floodplain features, is that 2 meter resolution needed everywhere, for instance on flat floodplains or valley sides? The key overhead in this project was the output of the same resolution throughout the whole model domain. We think about hydraulic modelling with uniform grids. It's very easy to use. From a user perspective, the only decision is the uniform cell size, and this is then applied across the whole model domain. Use of uniform grids makes the engine code simpler. It also has a regular memory access pattern, and this leads to quite a fast solution in terms of time per cell per step. The downside is the very nature of that uniform grid. This means that to represent any areas in detail, for instance, where there might be rapidly varying topography, where there's particular hydraulic features, or where particular flow paths require additional resolution, detail must be added everywhere within the model domain, even if it's not actually required. The square grids, oblique flows can also cause an issue. So in our experience, flows at 45-degree angles tend to lead to numerical diffusion, particularly for first order schemes. And therefore, there's often a requirement for second order interpolation, which is a little bit more complex to code. We've also done testing within deep wall channels, which shows that convergence typically requires 6 or more cells across the feature width. And again, if we're trying to add in that resolution then gets applied to the whole model domain. We then have at the opposite end of the spectrum hydraulic modelling with an arbitrary mesh. So this allows users to spatially distribute the mesh resolution. With an irregular mesh, it's possible to align the mesh elements with the primary flow directions, which means that the problem I identified previously with the oblique flows is less of an issue. This means that first order schemes can be used. A user adjustable resolution leads to efficient memory utilization. It allows the user to represent detail where it is necessary, whilst maintaining a larger mesh resolution elsewhere in the model domain. An arbitrary mesh is much more complex to code, has irregular memory access, and typically is generally slower than a fixed grid scheme in terms of time per cell per step. There's also various practical aspects in terms of building a mesh. It can be quite time consuming. Users have a choice as to what data they want to represent at the particular model scale. In my experience, users do not want to be spending the time creating meshes. They quite often like to use mapping data, which, although fantastic as a mapping resource, is not particularly well suited for meshing. So when you use that mapping data to create break lines and other mesh features, or to spatially distribute roughness or infiltration, depending on the actual meshing scheme used, it can lead to the creation of very small mesh elements. And those very small mesh elements control the time step. And where you've got very small mesh elements, very small time steps, you can lead to very, very long simulations. Also, with meshes, it's not always possible to obtain mesh independency. Quite often there is a need to show the benefit of a particular flood alleviation scheme or an option relative to a baseline model. Modeling the option scheme involves different model geometries which will affect the local mesh, as you'd probably expect. But occasionally they can lead to subtly different meshes, or mesh configurations in more remote locations. The difference in mesh not only affects results locally, but can in some instances lead to differences in locations far removed from the area of the actual geometry modification. And that makes it problematic to assess the impact of an option or a flood scheme relative to a particular baseline. You don't tend to get that same issue with a fixed grid. So with that in mind, is there something in between which allows the user to take the ease of creating a fixed grid, the speed of a fixed grid simulation with its regular memory access, but also have the adjustable nature of a flexible mesh to allow the representation of detail where it's necessary, without applying that throughout the whole model domain? We think the solution could be in the Quadtree type solution. This allows an adjustable resolution, allowing the modeler to represent detail where necessary without the overhead of a fully fixed grid. It allows the user to specify multiple layers of reduction to allow further refinement of the fixed grid where it's required. The engine code is slightly more complex and the memory access patterns aren't as regular as you'd expect for a fixed grid scheme, but the scheme that we've coded still seems to be pretty fast. From a user perspective, there is more user input on where to refine the mesh, but not nearly as much time and effort as would be required for a flexible mesh. And we're actually looking at numerous ways of automating the use of Quadtree refinement, for instance, where there might be rapidly varying topography, for instance. The downsides are that it's still a square grid. Oblique flows still require a second order interpolation, which, as mentioned previously, is more complex than a first order scheme. Also, oblique deep wall channels can still be an issue, although with a Quadtree refinement, it should be possible to add sufficient resolution to resolve the hydraulics in those regions without having to add in the detail throughout the whole model domain. So to go back to the fixed grid, in terms of the continuity equation, with the fixed grid TUFLOW QPC scheme, a cell-centered depth is calculated and the velocity components at the cell faces are tracked with the finite volume scheme. We can see there the notation adopted in which the cell average quantities for the cell in question are shown by the black dots with the subscript CC. The neighbouring cells are denoted N1 through to N4, again shown by black dots. Water depth changes in time were computed by considering conservation of volume as expressed in the equation, in which A is the cell area, H is the water depth, and SQ is any volume source or sink connected to that cell. So we're talking things like inflows, direct rainfall, and infiltration. The cell wall volume fluxes, phi 1 to 4, across each face are calculated based on velocities. And we've got the U velocities shown by the red crosses and the V velocities shown by the green crosses there. The computed derivatives for H, U, and V are local in time and may be computed for each cell independently of other cells. That means that the calculation steps are highly independent and then can be distributed across multiple CPU and also onto GPU cards. Apologies for that. With the TUFLOW Quadtree scheme, each cell can have a maximum cell division of 2 across adjacent cells. So neighbouring cells can have 2 times more cells or 2 times less cells. This results in 1 to 2 faces per cell side. So if we look at the cell in question there, on the left-hand side we have 2 fluxes into the cell, and on the right-hand side we have 1 flux out of the cell. Again, towards the bottom of the cell, we have 2 fluxes in, but only 1 flux out of the cell at the upper edge. So we can actually have the same source term as previously, but now we can have up to 8 side fluxes per cell to feed into that continuity equation. So we've been coding up the Quadtree scheme, and it's currently being internally benchmarked prior to release. We've run the scheme with a number of benchmark tests, and I'm going to show you a couple of those now. One of which is the UK Environment Agency benchmark test. probably one of the more robust test data sets that's available. Of all the tests, though, it's only really test 6A which has any observed data to compare it to. Test 6A, if you're not familiar, is one in which a reservoir breaches into a confined channel, and then there's also a downstream obstruction represented by the red rectangle in the center of the image. The model is highly transient with supercritical flow and moving hydraulic shocks. It's a very good model to test the TUFLOW Quadtree engine on. The image shows the various levels of Quadtree refinement with 5 areas of differing grid resolution, which you could probably just about make out by eye, together with the mapped velocity. There's a number of hydraulic features within this model. Just upstream of the obstruction, we have a hydraulic jump, and that hydraulic jump propagates upstream as flow eases as the reservoir drains down. Downstream, we've got the obstruction wake and eddy shedding downstream of that obstruction. The TUFLOW Quadtree scheme seems to reproduce the hydraulic jumps quite well, and we don't see any edge effects where the mesh resolution changes. There's minimal reflection as the mesh changes from coarse to fine and vice versa. Another example is wave transmission on a flat surface. In this case, we have 3 levels of Quadtree refinement with the highest resolution in the center of the square domain. We can see the depth as it passes through the varying grids of different sizes, and there's no lag effects as momentum and mass is conserved across the internal boundaries. Traditionally, within the CFD community particularly, people tend to stay away from sudden transitions in grid configurations and try to smooth out the transition in grid size. However, as we can see here, we have very minimal reflection again at the boundaries, which suggests that the TUFLOW QPC scheme is behaving pretty well despite that relatively sudden change in grid cell size. So we're continuing the benchmarking, and we're pretty confident that we'll be able to get TUFLOW Quadtree out to our users at the latter part of this year. In terms of what are the potential applications, urban drainage is probably the most obvious example. Surface water, either from fluvial sources or surcharging pipe networks, tends to accumulate on road surfaces, which behave like open channels in terms of routing flow. Typically, you would want 6 or more cells across the width of a feature to represent that conveyance, so six or more cells across the road. And with TUFLOW Quadtree, this can be represented without applying the same resolution throughout the model domain. We tend to think of roads as flat surfaces, when in reality there is a lot of road topography. So particularly things like road cambers and cross slopes. These are very important in terms of road drainage. They feed into inlets and grates, which drain the flows from the 2D surface, from the road surface. We've also got the dropped curbs, which are often a key feature in terms of property flooding, particularly where the property level might be lower than the road level. And we also want to represent flow around buildings in an accurate manner. Also, increasingly, we're wanting to represent sustainable urban drainage features explicitly within model domain, and being able to use Quadtree refinement to refine the grid in those locations will certainly help do that. We can see on the right-hand side the effect of grid size on the flood footprint and water surface elevations. Increasing the resolution obviously improves the representation of the underlying topography, and we can see that results converge on a solution there. If we were to use the first grid size, which is 20 meters, this would use 7,500 cells. If we use a 0.5 meter grid cell, uniform across the mesh, that would use 12.5 million cells. Using the Quadtree solution, we reckon actually we can reduce the number of cells required by 75%. And actually in this instance, we would only need to use 3.1 million cells by using that 0.5 meter grid selectively throughout the model domain. And we've done similar tests on similar models, and we reckon it's about 75%. That 75% reduction in number of grid cells reduces the system RAM requirements by about a third, and actually can lead to run times which will be 3 to 4 times faster than you would expect with a uniform grid throughout the whole model domain. The other examples or applications is on rural environments or fluvial environments, so dam break and fluvial catchments. This video is one that's been publicly available for a while, and it shows the application to a dam break scenario with 3 levels of nested grids. We can see the flood wave propagate down through the valley, through the channel, which is represented with the finest level of grid size, and then we've got the functional floodplain represented in an intermediate level of grid. The final level there is the wider valley floor, which wouldn't normally be utilized except in a more extreme event, such as that which might occur with a dam break further upstream. So in terms of a fluvial environment, the Quadtree solution will be quite useful in terms of representing the detail in channels, particular floodplain features, structures, openings in embankments and things like that, and also natural flood management options. We'll be finalising the benchmarking, and we're currently in the process of developing the input-output side of the TUFLOW Quadtree engine, but all things going well, this should be available in the latter part of 2019. So just to summarise, the Quadtree solution is one that sits between the common fixed grid approaches and the flexible mesh schemes. It has many of the benefits of the fixed grid scheme, whilst allowing the user to represent detail where appropriate. It has the efficient memory utilization that the flexible mesh scheme has, but with an easier mesh generation process than an arbitrary mesh. And we'll be looking into adding some automation tools to speed up that process for our users. The TUFLOW Quadtree engine uses the same explicit finite volume solution as TUFLOW HPC, and that TUFLOW HPC has proven conservation of volume and momentum, has excellent cell size convergence and simulation stability. TUFLOW HPC is designed to be run on multiple CPU and to take advantage of the significant speed gains on GPU cards. It can also be distributed across multiple GPU cards to allow the running of very large models. So we've seen models upwards of 400 million grid cells. The application for TUFLOW Quadtree is for users in urban environments, particularly direct rainfall, where users are likely to represent the detail on road surfaces, to represent primary flow routes and also drainage features, but also applications to large catchment modelling, where again quite often direct rainfall is applied, where users will want to represent the detail with natural drainage features. So thank you very much for listening, and I'm happy to take any questions.
Thank you, Duncan. That was a very interesting presentation. So I think if people would like to type into the message section, conversation section, if they have a question, and then we can select somebody to. Does anybody have any questions? Certainly a lot of interest today. It's a very interesting presentation. I think I'll ask one whilst people are thinking about it then. So you said the model is conserving momentum, and that's quite interesting because not all urban models do conserve momentum under the assumption that it's largely negated by frictional forces.
Well, primarily the model itself is based on sort of rural floodplains and channels. So it comes out of Australia, where a lot of the channels are strongly three-dimensional, not strongly three-dimensional, but require the conservation of momentum within that, because it's quite important. You've got quite a few different forces going on there.
Yeah, quite, especially things like dam breaks. Like
exactly,
that.
Yeah.
So we've got Ballard Chad, who's asking about licensing options. Will it be similar to HPC or separate solver?
So in terms of the licensing, the QPC solver will require the M2D multiple 2D domains module. If you have that, then the TUFLOW QPC will be part of that as standard. If you want to run it on a GPU card, you will need the additional GPU module as well.
Okay, cool. And we've got Sam Jameson, who asks, any plans to refine the Quadtree dynamically according to the current flow processes?
Not currently at the moment. That might be something we look at a bit further afield, but for the moment it's just a case of getting that out in a static manner.
Would be interesting. got one last question coming there. Maybe? So did you say, is there any automated way to actually generate the mesh at the moment, or?
We are looking into that at the moment. We've got a few ideas of what we can do, particularly with rapidly varying topography. But yeah, I can't comment on the detail on that just at the moment because we're still at the very much at the ideas stage with that one.
Okay. And yep, Arnold Kosh asked, thanks for the interesting presentation. Did you test real-time modeling with this solution?
We haven't tested real-time modeling with TUFLOW QPC or Quadtree just yet. We have with TUFLOW HPC. I guess this will be something that will be another application once it's released to users more widely.
Be interesting.
But it certainly lends itself to that real-time environment just by reducing the number of cells and like I said, speeding up the simulation. Which always helps in those real-time applications. The quicker the simulation.
Imagine in some circumstances you are already quicker than real-time. So it's yeah, finding those circumstances, I imagine. So Navian Ramilian, sorry about the pronunciation, asks any comments on runtime gains?
So yeah, we reckon in the typical urban environment you'll be looking to. Sorry, I just need to check back over one of my notes. I think we'd be looking at 3 to 4 times faster, just as a consequence of the sort of reduction in the number of cells required to represent the detail across the whole domain.
Compared to a uniform grid, I guess.
Compared to a uniform grid across the whole domain. That will obviously depend on the application as well. I think the urban environment probably the best case.
It's interesting. I was going to ask, are there any cases where, because of course you've had to code the Quadtree system in, that it's going to be less efficient?
Interesting question. It's not something that we've come across at the moment. I
suppose the increase in efficiency from having less cells generally compensates for that.
Yeah, it's not something I've considered myself, but yeah,
it's interesting.
Not something I'm aware of currently.
Any more questions? So I think if we haven't got any more questions there, then I shall close the presentation floor. Thank you very much, Duncan.
Thank you very much, Mike, and thanks everyone for taking the time to listen again.
Thank you. Cheers very much.
Cheers, thanks.